Greetings everyone, and welcome to a lecture in Engineering Numerical Methods. This is covering Lecture 5. And in Lecture 5 we are going to be moving into Chapter 4 of our textbook, which is Numerical Methods for Engineers and Scientists. Specifically, this is for solving a system of linear equations. We're going to look at a couple of methods that encompass both work in MATLAB and work by doing it manually. Much of this will be familiar to you from linear algebra, so I think we'll cover it reasonably quickly, but there will be a couple of programs to type in. When we reach those points in the video, please pause, type in program, so that you can then have the experience of running it, debugging it, all of that stuff that's very beneficial to you in building up your array of toolbox tools, and in also getting used to working with MATLAB, so you can do it here instead of trying to puzzle it out in the middle of a test, which is never much fun. So today we're going to definitely cover section 4.1 background. We will talk about the Gauss elimination method, which again should be pretty familiar to you from your linear algebra classes. Some of the problems with Gauss elimination lead to Gauss elimination with pivoting, so we'll talk about that. We'll speak about Gauss-Jordan elimination a bit and the LU decomposition, and we may touch on the inverse of a matrix. Please note that if you have the second edition of our textbook, this chapter actually covers eigenvalues and eigenvectors. However, in the third edition, which is the official for our class, this is moved to a different chapter, so we will be covering that topic later on in the course. So let's start out with just a little bit of background. In engineering, we often come across problems that can be described as a series of simultaneous equations. These equations would then be broken up into things that have a coefficient and a variable. We will number those coefficients in such a way that we can readily identify them with the equation they're part of and with which variable they go. And each of those equations then has a solution. This is often rewritten in matrix form, where all of the coefficients for the equations make up what's often called a matrix, and all of the solutions make up what is often called a B matrix. There are a number of different techniques that we can use to solve this kind of system. Direct methods use arithmetic operations to calculate the solution. These are very, very easy and very effective as long as your matrix has a form that's either upper triangular, lower triangular, or diagonal. We'll talk about what each of those is in just a moment. If your matrix is not in that form, though, then we may have a problem that's a little intractable, and as we've discussed before, that's exactly where you want to use numerical methods. In numerical methods, then, we generally perform an iterative method. This gives us an approximate solution, and then we can iterate to improve it. So, let's talk about some of the direct methods first. The direct methods always try to get our problem into one of these three formats. An upper triangular is a format where all the coefficients below the diagonal on our A matrix are 0. We can then use back substitution to start at the end of our chain of variables x sub n to calculate a coefficient, and then use that to go back and calculate each variable value for our final solution. Similarly, we can create a lower triangular matrix where all of the coefficients above the diagonal are 0, and this can be solved by forward substitution. So we start with our first variable, solve for it, and then continue on. My favorite, and probably yours as well, is a diagonal system which has non-zero coefficients only along the diagonal. And my favorite, of course, is because it's simple to solve. So in these direct methods, the first one we're going to look at is Gauss elimination. This one is fairly intense from the standpoint of doing it by hand. We will have a sample problem or an example problem in the book that has actually a separate PDF file, which you can find on Canvas. And I would urge you to read through this and refamiliarize yourself with it. I say refamiliarize yourself because this is covered in depth in your linear algebra class, or at least it always has been. So what I'm going to go through here should be just a review. Now this is a very old method. It was first described in some Chinese texts around about 2,000 years old. It was written of by Isaac Newton in 1670, but the guy who got the credit for the name was Gauss. He devised the standard notation that makes it a little bit more tractable, and so his name got tagged to it. This manipulates our linear equations so that we're in upper triangular form, which then allows us to do a back substitution for a solution. So, in every case, we look at a series of n equations, which should then have a series of n unknowns, the same one. The method will take n minus 1 steps. So if you have a very long system, this becomes a very long problem to solve by hand. In step 1, what we're going to try and do, and I'm not going to read through this whole thing because you can read it faster, is get rid of the term containing the x1 variable in every equation except for the first one. You can then imagine we'd get rid of the term for x2 in every equation after the second, x3 in every equation after the third, and so on. To do this, what we do is select a pivot equation. For step 1, we use the first equation as our pivot equation, and we create then a pivot coefficient. The steps to do this are listed below, and please note that each of these pivot coefficients has a specific name and is created with a specific formula. So when we create these, actually, it's worthwhile holding on to them because we'll see an area where they can be used in a later direct method. So I'll let you read through step 1. We'll go down and take a look at each of these pivot coefficients. So you can do this quite quickly by going ahead, setting up your system, and creating each of these pivot coefficients. Now, please note that the operations on a solutions matrix B follow the same pattern as the operations that we perform on A sub n. Step 2, as mentioned in this particular system, would be to eliminate the x2 term in the third and fourth equations. It follows the same basic type of pattern. Please note that we do have pivot coefficients generated here. Step 3, then, in the third equation, using the pivot equation, we try to eliminate the variable x3 from the fourth equation. And you can see that as we step through this, we are creating an upper triangular matrix. So then we can use this last equation down here in order to back substitute. So we would get a value for x4, substitute it in to the previous equation, a value for x3, substitute x3 and x4 into the equation with x2, get a value for x2, and then finally we can solve for x1. I do urge you to take a look at the PDF file for example 4-1. This is on page 106 in the third edition of the book. Please take an opportunity to review that. In the meantime, after you're done, we can go on and take a look at the program that we're going to use in order to solve this kind of thing. This is example 4-2 on page 108. I'm going to flash the program up on the screen. Please pause at this point so that you can type in the program and try it. Alright, so if you've restarted the video lecture at this point, you can see that the program we're using to solve the Gauss method is actually a function, and it's fairly short. Which makes sense, because if you look back at all of those equations for the pivot coefficient, those are all a very predictable pattern, so we can use a nice simple for loop to generate each of those coefficient changes. In order to use this particular program, we would call it with a series of function calls. So, I have created a very basic program here which calls it. You'll note that I have commented out the actual call. If you type this in, go ahead and uncomment one of them. What you'll get then if you run it, let's go ahead and open this up. I will get a very nice solution for A, and this is done using the Gauss method. Obviously, much easier to let MATLAB perform all of those pesky calculations than it is to use your calculator and perhaps your fingers, like I would generally do. Now, there are a few potential problems with Gauss elimination. Obviously, if you have a pivot coefficient that is 0, you cannot divide by 0, and so the Gauss method can't be used. If your pivot coefficient is very small relative to the other terms in your equation, then you can get significant rounding errors. Now again, whenever we talk about error in numerical methods, the question is that error something that we worry about? The answer is always it depends. You need to look critically at your engineering judgment of the system in order to determine whether the error that you're likely to get is going to be a significant factor in how you use your solution. If you have one of these two problems, a way around it is to use what's called Gauss elimination with pivoting. This reorders the equations on the fly, so actually as you're going through, to solve problems with Gauss elimination. We can see this in example 4-3 on page 113. I'm going to go ahead and pull up the equation or the program that goes with that. Here's the function that does Gauss elimination with pivoting. Please again pause the video at this point so that you can type in this function and try it out. Alright, hopefully now you've got a fully debugged nice function. You can go ahead and try changing this. Go ahead and use pivot. So I'll try Gauss pivot. And you see we get the same solution in this particular instance. The problem is not such that we have a major issue. But do take a look again at that section of the book, that particular example, so that you can fix it firmly in your mind. Alright, continuing on. So Gauss elimination, which we've just covered, modifies the system so that you get an upper triangular, and that allows you to solve by back substitution. There's a modification on this called Gauss-Jordan, which modifies the system to be my absolute favorite, diagonal. In order to do this, the pivot equation is normalized by dividing all of the terms in the equation by the pivot coefficient, And then the pivot equation is used to eliminate all of the off-diagonal terms. This is done in example 4-4 on page 116 in your book. This one again is done by hand. I have a PDF file up that describes it. You can also look in the book. Please pause the video at this point, read through it, try it a little bit on your own to make sure that you're comfortable with the method. Next thing we're going to talk about is called LU decomposition. This would be lower and upper triangular decomposition. Now, with Gauss and Gauss-Jordan, we need to modify or manipulate the solution matrix in order to solve the system. So, if you have more than one potential solution matrix, this means that you end up repeating these fairly long processes with multiple solutions. And this obviously can be quite tedious if you're doing it by hand. If you're doing it, though, with a computer, perhaps not as much of an issue. However, many of these numerical methods were put together in order to make systems much easier to solve when they were being done by hand. That's what LU decomposition does. It works only on the coefficient matrix, the A matrix. Conceptually, what it does is, for our system, which is the coefficient matrix multiplied by the variable matrix is equal to the solution, we decompose that coefficient matrix into an L and a U matrix, such that when we multiply L and U together, we get back to our original coefficients matrix. Therefore, we can substitute in the L and U matrices in place of the A matrix, which gives us a way then to solve very quickly for any given solution matrix or B matrix. Now, you remember when I mentioned earlier with the Gauss elimination procedure that we might want to keep track of all of those coefficients and pivot coefficients that we created. This is the reason why we actually calculated all of the elements needed for the L and the U matrices when we were performing Gauss elimination. So this again is a very simple setup. We can take those coefficients for Gauss, plug them into our L and U matrices, and we have a solution. Alright, we will pick back up with section 4.6 in this chapter on Thursday. Thanks for watching, and I look forward to seeing you in our next class meeting.